Let us start. Limit of f of xy at x0, y0. We have already seen the simple examples of limit of f of xy when xy tends to x0, y0. And how do we evaluate this kind of example? Now we shall look at the geometric meaning of limit of f of xy at point x0, y0. But before starting this, let us see what is limit of f of x at point x0. As you know that you are writing the same thing in the symbolical way. Limit x tends to a f of x. If it exists, then it is L. So what do we mean by when the limit exists at point A? This is x, y, and suppose this is the function f of x, and this is the point A. So now when do we say x tends to A? Then x tends to A or x tends to A, and then the corresponding value is this one, and this point is L, right? So here we have only two paths. Either path number one is x tends to A plus, and the another path is x tends to A minus. We don't have any other path because x-axis is the real line, right? But now suppose we have given the surface z is equal to f of xy. Then what is the definition of limit? The definition of limit is, I'm writing only the few lines here, a few terminology here, not the full line. We say that we say that f of xy has a limit L at point x0, y0 if for every epsilon greater than 0 there exists delta greater than 0 such that 0 less than mod such that f of x minus L, its absolute value is less than epsilon whenever we say that 0 less than xy minus x0, y0 is less than delta. Now here this is important. What is this? This is actually the distance between the arbitrary point xy to x0, y0. It should not be more than delta. So what is the distance between 2 points in R2? So the distance formula is this: under root x minus x0 square plus y minus y0 square is less than delta. Now if I take square both sides, then this is nothing but x minus x0 square plus y minus y0 square is less than delta square. Here I am writing 0 less than, 0 less than. But now if you consider only this particular quantity, x minus x0 square plus y minus y0 square equal to delta square, then what is this? This is nothing but the circle with center x0, y0 and radius delta, right? That means on my domain, I have to take the disk because this is less than delta square and 0 is less than. That means I take the disk and remove the center point, right? X0, Y0. So for example, uh, suppose let me try to draw the structure. Just trying. So this is X, this is Y, and this is 0. Suppose this is the center X0, Y0, and this is the circle, right? So center X0, Y0, which we are going to remove, and all the points X1. This is the radius delta. Now what I do, now say this is my Z axis, right? This is my Z axis. And if this is the surface, then what we do, we find the value of each point here. So now when this particular xy is near to x0, y0, then this value should go near to this, right? Now let me explain how does it look like actually. So say this is the surface. The red color is the surface, right? And somewhere to this -1, somewhere here it is the circle, right? So that I have mentioned here. Look at this one. Now suppose somewhere this is the point x0, y0, somewhere here, right? And then, so this is a circle corresponding to this one. This is my x0, y0, and suppose this is a circle with the radius delta. And corresponding to all these points, we find the values of delta. Sorry, value of the function. Then all these values are here. Now f of x0, y0 is this particular value, this. Now when all these xy are going near to delta, then the corresponding values should go near to this value f of x0, y0, right? So here what is the situation? The situation is, here we had only two paths. Only two paths. One path is this and another path is this. Because the domain is only a line. Whether here we are moving on the plane. So on the plane, what is the situation? These are the random points xy and this is the point x0, y0. So now suppose you have to go from this point to this point x0, y0. How many different ways you have? This is one way. You are going direct to straight, or you may go to this way, or you may go to this way, you may go to this way, or this way, or sometimes this kind of way also you may choose. That means there are infinitely many paths from the point xy to x0, y0, and we have to look at all these infinitely many paths, right? So sometimes to find the limit at particular point x0, y0 is not that much easy task, but there is one particular method which gives us guarantee that the limit does not exist. For example, let me mention this exercise over here. Prove that prove that limit xy tends to 0 0 x minus y upon x plus y does not exist. So how do we prove this thing? That means what we have given here. Say this is the center 0 0. I am choosing any one very near point to 0 0. This is random point xy. When xy is going to 0 0, I have to check what is the value of x minus y upon x plus y. Now, in how many ways we can reach from xy to 0 0? As I told you that this is the one way, this is another way, this is one more way, one more way, one more way, right? So suppose I choose this path of the line, right? Because you know what is the equation of line? Y is equal to ax plus b. This is the equation of line, right? Now when the line is passing from the origin, b is equal to 0, so y is equal to only x. This is the set of lines passing from the origin, right? So suppose I am taking this path out of this infinitely many paths. Choose y is equal to mx for any m belongs to R. Therefore, limit xy tends to 0 0 x minus y upon x plus y. This becomes limit x tends to 0 x minus what is y? Y is mx upon x plus mx. So this is limit x tends to 0. If I take x common, then 1 minus m upon x common, then 1 plus m. So I can cancel out x and x. So next what do I have? The remaining thing is only 1 minus m upon 1 plus m. Now what does this mean? When I am choosing this line, then the value of the function is 1 minus m upon 1 plus m. Now suppose m is equal to 1. That means I am choosing this line y equal to x. Then what is the value? 1 minus 1 upon 1 plus 1, which is 0. If I choose my path to y equal to 2x instead of y equal to x, then it becomes 1 minus 2 upon 1 plus 2. So this is minus 1 upon 3. Again, if I change my path from say m equal to minus 5, that is y equal to minus 5x, then my value is 1 minus minus 5, which is 1 plus 5 upon 1 minus 5. So this is 6 upon minus 4. You can cancel out 2 here if you want. But what I mean is when m is changing from 1 to minus 5, then the corresponding value of the function is also changing. That means this answer 1 minus m upon 1 plus m fully depends on which path we are moving, right? So this answer is not unique, and once this is not unique, we cannot say that limit exists, because for the existence of limit 1 minus m upon 1 plus m must be unique. Here it is not unique, right? So how do we write here? Therefore limit xy tends to 0 0 x minus y upon x plus y depends on m, and therefore limit does not exist. Clear? Now let us discuss another exercise. Check whether the limit of f of xy is equal to x raised to 4 minus y square upon x raised to 4 plus y square exists at 0 0 or not. Okay, now how do we solve this one? What I want to check, limit of xy at particular point x raised to 4 minus y square upon x raised to 4 plus y square. This exists or not? Okay, now you see which kind of path I have to choose here. So now here I apply one trick, because in the last exercise we have chosen the path y is equal to mx, but here with which path we are working? Suppose I choose y is equal to mx, then what happens? So let me just check it. If I choose y is equal to mx, then what happens? X raised to 4 minus y square is m square x square upon x raised to 4 plus m square x square. I can cancel out x square, so this becomes x square minus m square upon x square plus m square. And when x tends to 0, this is minus 1. Right. But these are not the only paths. We may work with y is equal to m under root x. We have the another path mx square. So these are the paths we have. Right. We may have mx cube. We have to look at all these different paths. So over y equal to mx, we have answer minus 1. That doesn't mean that the same answer we would have over all these paths. Right. So what happens if I choose the path y is equal to mx square? Right. So suppose I am taking the path y is equal to mx square. Then what happens? So this is limit. I am writing what is the variable x for y. X raised to 4 minus y equal to mx square. So what is y square? M square x raised to 4. So m square x raised to 4 upon x raised to 4 plus m square x raised to 4. Now here we have only one variable x, so I am writing x tends to 0, because whenever x tends to 0, then x square tends to 0, then mx square tends to 0, and mx square is nothing but y, so y tends to 0. Right. Now take x raised to 4 common, so this is nothing but limit x tends to 0, 1 minus m square upon 1 plus m square, which is 1 minus m square upon 1 plus m square. The same situation occurs here. Here we had 1 minus m upon 1 plus m, whereas here we have 1 minus m square upon 1 plus m square. So now how do you write? So here the limit depends on n, right? And therefore the limit does not exist. Limit does not exist. So these are the simple examples on which you need to think that which path you have to choose. For few examples, y equal to mx will work. For few examples, y equal to mx square will work. There may be some example for which we need to work with y is equal to mx raised to say 1 upon n, right, for some proper value of n. For example, suppose my f of xy is of this kind, x raised to 1 upon 2 plus y raised to 1 upon 2 divided by x raised to 1 upon 4 plus y raised to 1 upon 4. Then for which part you are working, y is equal to mx raised to what? This you have to think. In the next video, we shall discuss now the partial derivative of the function.